When people hear the term artificial intelligence, they often imagine futuristic machines that think and behave like humans. Popular culture has filled the concept with images of autonomous robots, digital minds, and machines that possess awareness or intentions. In engineering practice, however, artificial intelligence refers to something both more practical and more specific. Artificial intelligence is a branch of computer science that focuses on building systems capable of performing tasks that normally require human cognitive abilities. These tasks include recognizing patterns, interpreting language, making predictions, solving problems, making decisions under uncertainty, and learning from experience. To understand what artificial intelligence actually is, we first need to clarify what we mean by intelligence in general. Human intelligence is not a single ability. It is a combination of multiple capabilities that allow humans to interact with the world. Humans can perceive information through senses such as vision and hearing. They can interpret complex signals, including spoken and written language. They can recognize patterns, reason about relationships between objects or ideas, and plan actions that achieve specific goals. They can also learn from past experiences and adapt their behavior when circumstances change. Artificial intelligence attempts to reproduce some of these capabilities using computational systems. The goal is not necessarily to recreate human consciousness or awareness. Instead, the goal is to build systems that can perform specific cognitive tasks effectively. In other words, artificial intelligence focuses on the functional aspects of intelligence rather than its biological origins. From an engineering perspective, artificial intelligence can be described as the design of algorithms and systems that transform data into decisions, predictions, or actions in ways that resemble intelligent behavior. This definition highlights several key components. First, AI systems operate on data. Second, they apply computational processes to extract useful information or structure from that data. Third, they produce outputs that can guide decisions or actions. One of the most important aspects of artificial intelligence is that it is not a single technology. It is a broad field that includes many different methods and approaches. These approaches range from rule-based reasoning systems to modern machine learning architectures that contain billions of parameters. Each approach reflects a different attempt to model or approximate aspects of intelligent behavior. Historically, the earliest AI systems were based on symbolic reasoning. Researchers believe that intelligence could be achieved by representing knowledge in symbolic form and then applying logical rules to those symbols. In these systems, knowledge about a domain was encoded explicitly by human experts. For example, a medical diagnosis system might contain thousands of rules describing relationships between symptoms and diseases. In a symbolic AI system, reasoning occurs through the application of logical inference. If a patient has symptom A and symptom B, and there exists a rule stating that A and B together suggest condition C, then the system concludes that the patient may have condition C. This approach resembles formal reasoning in mathematics and logic. One major challenge was that human knowledge often contains ambiguity, uncertainty, and exceptions. Real-world situations rarely follow perfectly defined logical rules. Additionally, maintaining large rule-based systems became increasingly complicated as the number of rules grew. Conflicts between rules, incomplete knowledge, and unexpected inputs could cause the system to behave unpredictably. These challenges motivated researchers to explore alternative approaches to artificial intelligence. Instead of attempting to encode intelligence directly through rules, researchers began investigating whether machines could learn patterns from data. This shift in perspective gave rise to the field known as machine learning. Machine learning represents one of the most significant developments in the history of artificial intelligence. In machine learning systems, the programmer does not explicitly specify all the rules that determine behavior. Instead, the system learns those rules automatically by analyzing data. To understand how this works, consider a simple example. Suppose we want a computer to recognize whether an image contains a cat or a dog. One approach would be to write explicit rules describing the physical characteristics of cats and dogs. However, describing every possible variation of these animals in rule form would be extremely difficult. A machine learning approach takes a different strategy. Instead of defining rules, We provide the system with a large dataset of images that are already labeled as either cat or dog. The system then analyzes these images and attempts to discover patterns that distinguish the two categories. Over time, it learns statistical relationships between image features and labels. The model used in this process contains parameters, which are numerical values that determine how the model processes input data. During training, these parameters are adjusted repeatedly in order to minimize the difference between the model's predictions and the correct labels. This process is known as optimization. Once the model has been trained, it can analyze new images that it has never seen before and predict whether they contain a cat or a dog. Importantly, the system is not relying on explicit rules written by humans. Instead, it has learned patterns from the data itself. Machine learning introduced a fundamental shift in how engineers think about intelligence in machines. Instead of programming intelligence directly, engineers design systems that can discover patterns and relationships through experience. In this sense, machine learning systems resemble certain aspects of human learning. Within machine learning, several major categories exist. One of the most common is supervised learning. In supervised learning, the training data includes both inputs and correct outputs. The system learns a mapping between the two. Examples include image classification, speech recognition, and predicting house prices from property features. Another category is unsupervised learning. In this case, the training data does not include explicit labels. Instead, the system attempts to discover structure within the data. For example, it may group similar data points together in clusters or identify patterns that reveal underlying relationships. A third category is reinforcement learning. In reinforcement learning systems, an agent interacts with an environment and learns by receiving feedback in the form of rewards or penalties. Over time, the agent discovers strategies that maximize its cumulative reward. Reinforcement learning has been used in applications ranging from robotics to game-playing systems. As machine learning techniques evolved, researchers began developing increasingly powerful models capable of learning more complex patterns. One of the most influential developments in recent decades has been the rise of neural networks. Neural networks are computational models loosely inspired by the structure of the human brain. The brain contains billions of interconnected neurons that communicate through electrical signals. Neural networks attempt to capture a simplified version of this idea using mathematical structures. In a neural network, information flows through layers of interconnected units called neurons or nodes. Each connection between neurons has an associated weight, which determines how strongly one neuron influences another. During training, these weights are adjusted to improve the network's performance on a specific task. Early neural networks were relatively small and limited in their capabilities. However, advances in computing power, data availability, and algorithm design eventually enabled researchers to build much larger and more complex networks. This development led to what is now known as deep learning. Deep learning refers to neural networks that contain many layers of processing units. These layers allow the network to learn hierarchical representations of data. For example, in an image recognition system, early layers may detect simple features such as edges or colors. Later layers combine those features into more complex structures such as shapes or objects. This hierarchical learning process allows deep neural networks to achieve remarkable performance on tasks that were previously extremely difficult for computers. Systems based on deep learning now power technologies such as speech recognition, machine translation, recommendation systems, and autonomous vehicles. Another major development in modern AI is the emergence of large-scale language models. These models are trained on vast collections of text data and learn statistical patterns of language. By analyzing how words and sentences appear together across millions or billions of documents, the model develops the ability to generate coherent text and respond to questions. Language models operate using a principle known as token prediction. Instead of understanding language in a human sense, the model predicts the most likely next word or token given the context of previous words. Through this process, it can generate sentences, paragraphs, and even entire articles that resemble human writing. The scale of these models has increased dramatically in recent years. Modern models may contain billions or even trillions of parameters. Training such models requires enormous computational resources, often involving specialized hardware such as graphics processing units and distributed computing systems. It is important to understand that AI systems do not possess true understanding or awareness. They operate by recognizing patterns in data and generating outputs that statistically resemble patterns they have seen during training. This distinction is crucial for understanding both the strengths and limitations of artificial intelligence. AI systems can perform certain tasks extremely well when those tasks align with patterns present in their training data. However, they may struggle when confronted with situations that fall outside those patterns. This phenomenon is sometimes referred to as the problem of generalization. Another important concept in AI architecture is the idea of models and training processes. The model defines the mathematical structure that processes input data, while the training process determines how the model's parameters are adjusted. Training often involves large datasets and computationally intensive optimization procedures. Engineers must carefully design both the architecture of the model and the training methodology. Decisions about model structure, data quality, training algorithms, and evaluation metrics all influence the final performance of the AI system. Data plays a central role in artificial intelligence. The quality, diversity, and scale of the training data often determine how well a model performs. Poor quality data can lead to inaccurate or biased models. For this reason, data collection and preparation are critical components of AI development. Another aspect of AI systems is evaluation. After training, engineers must measure how well the system performs. This involves testing the model on data that was not used during training. The goal is to determine whether the system can generalize to new situations rather than simply memorizing the training data. Evaluation metrics vary depending on the task. In classification tasks, metrics such as accuracy, precision, and recall may be used. In language generation tasks, evaluation can be more complex because multiple outputs may be acceptable. One of the key themes that emerges when studying artificial intelligence is the interplay between algorithms, data, and computing power. Progress in AI has often occurred when improvements in one of these areas enable advances in the others. For example, larger datasets and faster hardware have made it possible to train more complex models. Another important perspective is that AI systems are tools designed to augment human capabilities. They can process large amounts of data, identify patterns that may be difficult for humans to detect, and perform repetitive tasks with high efficiency. However, they still require human oversight, interpretation, and guidance. Understanding what AI is therefore requires understanding both the technical mechanisms behind these systems and the broader context in which they operate. Artificial intelligence is not magic, nor is it a mysterious force that emerges spontaneously from machines. It is the result of carefully designed mathematical models, vast amounts of data, and extensive computational infrastructure. As we continue exploring the architecture and working principles of artificial intelligence, we will examine how these systems are built in practice, how modern AI models process information internally, and how different components interact to produce intelligent behavior. The next part of this presentation will move deeper into the internal structure of AI systems, focusing on how models are trained, how neural architectures operate, and how modern AI systems generate predictions and decisions in real-world environments.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.